Let w equal root 3 plus I over 2, and z equal -1 plus I root 3 over 2, where I is the imaginary root. Find the number of ordered pairs, r and s, of positive integers not exceeding 100 that satisfy the equation I times w to the r is equal to z to the s. Okay. So let's write out what these two complex numbers are. So we want to look for r and s such that I w to the r is equal to z to the s. My first instinct here is to rewrite w and z in terms of exponentials. They have the same modulus, and that immediately gives us a big hint as to what r and s can be. Let's make sure they have the same modulus, right? We have something of magnitude 1 over 2, something of magnitude 1 over 2, plus something of magnitude root 3 over 2, something of magnitude root 3 over 2. So w and z have the same modulus, meaning that these only have the same modulus if r is equal to s. Okay, so we've already reduced the question to the fact that r is equal to s. Then what we're going to do, if we write these in polar coordinates or in as an exponential, then we're just worried about the angles, the argument of things working out. Okay, so let's draw a triangle. And if I look here, this is for w. So here I have root 3 over 2. Here I have 1. So the modulus is going to be this squared 3 over 4 plus 1. That's a strange modulus, right? Well, it's going to be the square root of that, of course. Oh, sorry, this is 1 over 2. Okay, this makes a lot more sense. So I have 3 over 4 plus 1 over 4. So, yeah, these both of them have a modulus of 1. Oh, okay, hold on. If they have a modulus of 1, then what I said earlier is not true. Yeah, I did not think that these would have a modulus of 1. So r and s can in fact be different. Anyway, let's call this theta w. And theta w is equal to 30 degrees, right? Which is pi over 6. Okay, let's do the same thing for z. Z has a real part of -1/2, imaginary part of root 3 over 2. So again, the modulus is 1. We'll call this theta bar z because it's not exactly the angle we're looking for, but theta bar z is pi over 3. But what we really want is that angle. Call that theta z. Theta z is pi minus pi over 3, 2 pi over 3. Okay, so I can write w is e to the I pi over 6, and z is e to the I times 2 pi over 3. Okay. Need to take that into account. So let's just write out what this equation says. I w to the r is equal to z to the s. So I is equal to e to the I pi over 2. W to the r is e to the I pi over 6 r. And here I have z, is equal to e to the I 2 pi over 3 s. Okay, so on the left hand side I have pi over 6 r plus pi over 2, and on the right hand side I have 2 pi over 3 s, but these don't have to be equal, they only have to differ by a multiple of 2 pi. Okay, so let's get rid of the pi's and maybe multiply through by 6. R plus 3 is equal to 4s plus 12k. So r and s are positive integers not exceeding 100. These are from 1 to 100. And k is any integer. Huh. Well, if I think of this equation mod 3 or mod 4 or mod 12, maybe that can rule out a lot of values, a lot of potential values. If I think about this in terms of actual rotations, well, that's going to be hard because every time we increase this power, we rotate by this angle, pi over 6. Every time we increase that power, we rotate by 2 pi over 3. But there's this I thrown in there, which of course gives rise to the 3 here. I mean, I can see immediately one of the answers is that r and s are both equal to 1. Okay. Well, the right-hand side is even, meaning that r must be odd. And in fact, not only does it have to be odd, but it has to be one more than a multiple. The right-hand side is a multiple of 4. So we know that r is equal to 4m plus 1 for, I guess m is between 0 and 24. And will this now work for every one of these values of m? Right, let's try a few values of m. M is equal to 0. We have 1 plus 3 is equal to 4s plus 12k. 4 is equal to 4s plus 12k. Clearly s is 1 and k is 0, so this works. What if I say m is equal to 1? Then I have 5 plus 3 is equal to 4s plus 12k. So this gives 8 is equal to 4s plus 12k. And this works. S is equal to 2. M is equal to 2 gives 9 plus 3 is equal to, oh, hold on, but there might be multiple values of S. Sorry. For each value of M, there could be multiple values of S that work. Okay, so let's fix M. We have 4M plus 4 is equal to 4S plus 12k. Well, M plus 1 is equal to S plus 3k. Yeah, so M has to be between 0 and 24. That restricts R to be between 1 and 100. For a fixed value of M, we need this to be true. And S is also from 1 to 100. Man. Well, I guess there's always going to be approximately 33 or 34 values of S that make this a multiple of 3. Right? Doesn't matter what M is. Doesn't matter what M is. There will be values of S which make this a multiple of 3. It's a question of how many. And that will depend on whether M is 0, 1, or 2 mod 3. So let's write this mod 3. Then if M is equal to 0, then S is equal to 1 for, right, yeah, S has to be 1 mod 3. It can be up to 100. And in fact, this is if M is 0 mod 3. If M is equal to 1 mod 3, then S has to be from 2, 5, all the way up to 98. And if m is 2 mod 3, then s has to be 3 up to 99. So I need to count. Wait a minute. Can m be 25? No, right? 25 times 4 is 100, makes it 101. So if m is 24, this is 97. Okay, sure. So how many values of m are 0 mod 3? I don't want to get some mixed up off by 1, indexing error here. So is it 9 different values? Because if I divide these by 3, I have 8, 7, 6, 5, 4, 3, 2, 1, 0. Yes, there's 9 values. So m is equal to 0 mod 3, 9 values. And how many values of s are there in here? Well, this has 33 values. It's multiples of 3 from 1 to 33. This has 33 values because they're all just these ones minus 1, and this has 34 values. Okay, and if m is equal to 1, then we have m is equal to 1 mod 3. We no longer have 9 values, we have 8. 8 times 33, and m is equal to 2. We again have 8 times 33. So I think the answer is 34 times 9 plus 8 times 33 times 2. Okie dokie. So that's 306. 66 times 8. So I get 528 plus 306. I get 834. There are 834 ordered pairs that make this equation work. Whew. I don't really want to go back and check my work on this one. Obviously I would if this was if this had significant ramifications or something like that. Or if I had, if I were writing this test for real and I had the time, I'd go back and check a lot of stuff. But yeah, I think the approach here is pretty solid. Probably one of the best approaches you can take. So it boils down to finding numbers between 1 and 100 for R and S and any integer k that work here. Yeah, recognizing that R has to be of this form was nice. And then because k can be any integer, you're always going to be able to find, where did I write the general equation down? Yeah, k can be any k can be any integer. You're always going to find many values of s which hold for this. Sure. Okay. So anyway, that's my answer, 834. If that's wrong, then I'll let you know. And if I happen to figure out what my mistake is, if it is wrong, I'll let you know what that is as well. Thanks for watching.